In this video, we'll look at the answer key for Wednesday, April 22nd. And here we're looking at actual enzyme mechanisms now. So we talked about enzymes, we talked about general mechanisms. Now we're going to look at real mechanisms for two enzymes. And the reason why we look at these two enzymes is because they're well studied and they'll get you situated to look at any mechanism of any enzyme in the future. At least give you a basis to build your understanding of how enzymes work moving forward. Now, in the videos, the lecture videos, I go over the mechanisms in detail. Here, I'm not going to do that because honestly, it will just be me repeating myself. And since that's already in video format, I'm just going to more or less introduce the enzymes and then jump straight to the question. So if you haven't watched the lecture videos before coming to this one, I highly suggest you do to get the most out of this. So we're looking at lysosome, and lysosome is a protein that can cut sugars. Specifically, it cuts the peptidoglycan layer. Remember, the peptidoglycan layer is the sugar protein layer on the outside of bacteria. So lysosomes found in your saliva, found in your tears, and they will help to kill bacteria by cutting their outer wall. And it does so by cutting sugars D and E. So this NAM and NAG and ASP and GLU are enzymes that are active for this, while you have are amino acids, while you have other amino acids that help to stabilize our substrate. And our other protein that we focused on for this lecture was bovine trypsin. So bovine trypsin is a serine protease, and serine proteases, the mechanisms, we see that a lot for enzymes. So there are a lot of enzymes that use serine proteases. So that's why we study that mechanism as just an introduction to our serine proteases, where our catalytic triad here is ASP, HIS, and SER. So our first question is, let's go back to lysosome, and we mutate GLU to an ASP and ASP to a GLU. What would be the difference? Well, first let's think about these amino acids. The difference between GLU and ASP is really only a CH2 group. One case, you're taking away a CH2 group, GLU to ASP. In another case, you're adding a CH2 group, ASP to GLU. So in general, you're going to be changing how far away your catalytic amino acids are for the substrate. Now, lysosome has evolved over hundreds of millions of years, and it's very good at what it does. And the amino acids, ASP and GLU, are there for a reason. So if we start messing with the lengths of the amino acids, we're changing how far our substrates are away from our catalytic units. Therefore, we could expect the overall rate of catalysis to decrease. So another lysosome question. So GLU35 surrounded by hydrophobic amino acids. This raises its pK to 6.2. Why is this critical for lysosome's function? Well, if you looked at the mechanism, you would have saw that GLU35 is protonated. This is a little bit odd because GLU is normally negative. That's because GLU's normal pK is roughly 3.65. Inside the cell, it's very hard to protonate a glutamic acid. However, what the hydrophobic amino acids are doing, they're making glutamic acid not want to be protonated because that negative charge would be all alone. So in effect, the pKa has been raised, which means it's easier to protonate glutamic acid, which means that this mechanism can go faster. It's easier to do this mechanism. Our third question looks at lysosome and the amino acids that are around the substrate and not those participating in the catalysis directly. That is ASP101 and ARG114. Now, we need these for this catalyst to be successful, but they aren't actually the amino acids doing the chemistry. So let's say we take these and we substitute the alanine. If we look at the overall 3D structure, it really doesn't change, but the catalytic rate goes down a lot. Why? Well, if you look at ARG and ASP, they are forming hydrogen bonds to A and F. are terminal sugars. What they're really doing is they're helping to orient this sugar in the binding pocket so they're the perfect distance away from asp and glue, and they do this by hydrogen bonds. Alanine, the side chain is just a CH3, so it can't hydrogen bond, so it's really not going to interact with either A or F. That means that the sugar is not going to fit as snugly in the binding pocket as it does with asp and ARG. Since it's not binding as snugly, the distance between our catalytic residues could change, and it does change, and we see that slowing down of our rate. Now, I don't really have directed questions on serine protease because, like a lot of biochemistry, that's kind of pure memorization. So what I want you to focus on when it comes to test time, make sure you know the mechanisms we talked about. How do they work? What amino acids are involved in those mechanisms? During the mechanism, what is the transition state? How is the transition state stabilized? And why is it important to stabilize the transition state? And zymogens. What's a zymogen? Why isn't trypsin always active? Logically, why is it bad to have it active? And again, those were in the lecture PowerPoint that are up online already. So look over those, make sure you understand those questions. If you don't, please reach out to me. Otherwise, I will see you in the next video.